So we all agree that a 4-day week is better? Okay, so the week topic wasn't as popular. How about the new Drake album? Anyone listen to it? I'm just killing time so that I can prepare. So, Ryan, you didn't like the Drake album? Or albums? Basically, the complaining trio. Oh, they did me wrong. Yeah. They were okay. They were better than I expected, but it wasn't fun. I'm gonna give it 2 more minutes so that people can show up. Why is this? Oh, there's another song. You think we should remove days off on Saturday and Sunday and dedicate our lives to the craft 24/7? Yeah. A lot of people have to do that, right? We're getting towards that society. Although they're trying to I'm sounding like a conspiracy theorist, but I am. They're trying to just have AI be that, right? Something like that. Ideally, we want AI to work for us and then we just get paid to spend money. That's my belief. Universal basic income, and then just work is done by everything else. And then, yeah, you can spend 24/7 on things that you like. If you're an artist or something, I don't know. This will go on YouTube. So I was going to say, don't quote me on this, but I'm quoting myself on this. Whatever. It's one of those days. We've got 16 people. Any other topics we should discuss for a couple of minutes before we start? Okay. So this week, second week, was Fredo a tragic character? Fredo, which Fredo? Is it from one of them series? Am I missing something? I've been making slides all day because I've been busy and I have to do some other stuff. My brain is fried. Okay, let's put the Fredo conversation aside. We have some ground to cover, and then we can come back out to the Fredo conversation. I don't know what you're talking about, but okay. So yeah, today we're gonna do some math, like basically go over some mathematical concepts that it's useful for our data science work. But before we start, let's also look at the table. I've been updating. So we're here. And as you can see, now we have the chapters that you've got to read in the website. I haven't decided. I've said it's required and you should read them. And I'm going to Canvas is back so we can have quizzes. When I set up Canvas, I'm going to do little quizzes from the readings, and you're going to see where each of them comes from. So please pay attention to this, to the website. It's going to be on Canvas as well. But let's go back to the math. Okay, so probability is one of the more important things that we need to talk about when we're thinking as a data scientist. So essentially, it's a formal way to reason about how likely something that is to happen. The intuition behind it is on counting outcomes. So let's think about it. We think about an experiment, which is any procedure with a set of possible outcomes. And then, for example, we can think about rolling 2 dice, right? 1 red, 1 blue. I have die here, but it's Dungeons and Dragons. So for nerds like me, you could think about, I use it to predict the future. I actually predicted the Iran war twice. Anyways, I've been always correct. So yeah, you imagine that you have 2 die, 1 red and 1 blue, and then each face shows a number from 1 to 6, right? So we get as 36 possible outcomes, okay? 1, 1, 1, 2, 2, 1. As you can see, this is all the outcomes that we can have, okay? So each cell is 1 outcome, red die, blue die, and 36 outcome total, okay? An event is any subset of the sample space we care about. Okay, so for example, this is an event where the sum of the 2 die equals 7. Okay, so Highlighted outcomes all have red plus blue equals 7. There is 6 out of 36. Okay? And that's basically the probability of that event. 6 divided by 36. So outcomes in the event, total outcomes, right? Boom. We know we've got some probability going on. You probably, all of you have gotten this covered, but just let's go over it once so we have some basic understanding. So each outcome is equally likely, P136, and probability of E is the sum of probabilities of outcomes in that event, okay? So, and the probability is always sum to 1 across the full sample space. So for example, what is the probability of getting a dice total of 7 or 11? Because we care about 7, 11. And that's also like a game or something, I don't know. But again, you can just count 1, 2, 3, 4, 5, 6, 7, 8, okay? You can sort them to see like where they are in the whole thing, and then divide that by the total. Again, we get the probability of this event. Okay, how about at least one is even? Again, half of them, right? You can see all the rows. One of them is even, and then we can also say at least one is even, or is a 7 or 11, right? We can combine all sorts of events. But one thing that happens is that these two now have some shared, okay? You don't count the ones that are like doubly counted. So you get the probability of the first one, add the probability of the second one, and subtract the ones that are overlapped. That's how you basically don't double count, okay? And then you can also do an intersection of the two, right? These are the events where at least one is even and is a 7 or 11. So you can, again, look at the ones that are shared between two events and then calculate the outcome. This is 1, 2, 3, 4, 5 out of the total. When you do a union of both, you get the sum. Essentially, should be a very intuitive thing. It obviously gets more complicated. And again, I'm not even that good with a lot of it, but having this intuition of, hey, it's just mostly about counting is a good way to think about it. And I will be sharing a lot of videos on people that I like that explain these concepts. If you're interested, you can take a look at it. So how do we think about conditional probability? Imagine we're trying to think about this department, right? I'm just simplifying things. Imagine there are a lot of people who like games and there are a lot of people who like coding, right? And there are a lot of people who like neither, right? So what is the probability of meeting someone in CIAT that likes video games? Assuming this is all of CIAT. You just count all of these people who are within this circle, right? Look at this column. This is the people who like games. And then you take the sum of the, and that's 40, and then you divide it by the total number that is 70, and you get the probability. Okay? Probability of coding is the same. So you just look at this diagram, think about this diagram when you're trying to think about conditional probabilities, and then you get the sum. So there's a decent amount of people who like coding, but not as much, right? And then there is this intersection of these, right? There's probability of people who like games and coding. So this is this side of the visualization, right? This part, so that's 18. So you get 18 divided by 70, okay? Simple stuff. So thinking about conditional probability, let's think about this. We know a student likes coding. Does that tell us anything about whether they like video games? So let's look at this, right? So when we know that a person likes coding, then we're not looking at everyone else, right? We're only looking at the people who like coding, okay? So there's 30 total of them, okay? So from now on, because we know that that person likes coding, the denominator is 30. Okay? So what is the probability of someone liking games given, this is sign meaning given, that means that we know that they like coding. Okay? So this is the count of people that like games, and then you divide it by the people who like coding total. Among the 30 coders, there's 18 also like games. So probability of games given coding is 18 divided by 30. And also, if any of these I've been working on this, so if I'm doing some calculations wrong, maybe, or anyone, just let me know. Okay? So it's a bit higher than probability of liking games. So you say, okay, if you know someone likes coding, there's a higher probability that they're also gonna like video games. So basically, knowing someone codes makes them more likely to also like games. Okay? So this is the general formula. Probability of A given B is the probability of A and B divided by the probability of B. Very simple stuff. So to reiterate, both happen, 18, just B, all of people who code 30, and then you divide them, and then you get a number. That is the probabilities. Okay? And does it work? Is it the same as the other way? Let's look at it. Okay? So now, among 40 gamers, 18 also like coding, right? So this number doesn't change because that's the A and B. So what is the probability of someone liking coding given that they like video games? Okay? You do the same thing. You take the number of people who like coding, and then you divide it by the total. So comparing that to probability of coding, you can see that they're different, right? And also you can see that probability of games given coding is different than probability of coding given games. Again, it's important to be able to think about these concepts, even though you can calculate a lot of them. So how is this useful? I want you all to type your response, okay? Let's assume we know Alex. Alex spends hours analyzing what makes games work, talks about mechanics and level design, knows what Unity and Unreal are, and has strong opinions about why certain games succeed or fail, okay? Think about Alex. Do you think Alex is more likely to be a game developer or a content creator? Type your response. Game dev? I'm guessing that most people guess game developer. So let's look at it. Alex spends hours analyzing what makes games work, talks about mechanics and level design, knows what Unity and Unreal are, and has strong opinions about why certain games are succeed or fail. Okay? So most people guess that this is probably a game developer. But let's check. These are numbers that I searched. There's about 10 million game developers worldwide, but there's about 200 million content creators. Okay? So the ratio is roughly 1 to 20. Now let's consider these numbers. Okay? So let's think about just a hypothetical representative sample of 210 people in total. And let's say that 10 of them, based on this ratio, 10 of them are game developers and 200 are content creators. This is our population, okay? So our hypothesis, the hypothesis you guys gave me is that Alex is a game developer, okay? Alex is a game developer. This is the prior. The prior is how likely is H before we look at the description? How likely is that someone is a game developer, okay? So this probability of the hypothesis, again, just knowing that what is the likelihood, probability of someone being a game developer is 10 divided by 220, and that is this 0.048. Okay? That's less than 5%. But now we have the evidence. I have given you some evidence. The description of Alex is analyzes games, talks about mechanics, knows unity and unreal. So now we ask two questions. If Alex is a dev, how likely is this description? If Alex is not a dev, how likely is this description? Okay, so let's say that among 10 game developers, how many fit Alex's description? I would say 40%, 50% don't matter, right? So we're saying that probability of the evidence given the hypothesis is 40.4. Okay, we say that 40% of them, 50% of them, again, you decide, have that description. Not all game developers are nerdy, and I'm not a game developer and have that, right? So 4 out of 10 developers talk about mechanics, no unity, etc. The description fit developers pretty well. Okay? But what is the probability of the evidence given not the hypothesis? Okay, given the hypothesis is false. Okay, so among the 200 content creators, how many fit this description? Okay, even if it's 0.1, that would be 20 out of 200 content creators. Right? It's reasonable, right? 20 out of 200 content creators also talk about game design, no engines, etc. So lower rate, but there are so many more of them. And that is the idea, right? Everyone who fits the description is both of them together. 4 game developers, 20 content creators. We have 24 total that match the evidence, okay? So why is this helpful? Because now we know the probability of hypothesis given the evidence. Of the 24 who fit the description, how many are actually developers? Okay? 0.1. There's only a 17% chance Alex is a developer, given these ideas that we talked about. Despite the description fitting developers 4 times better, the base rate, this is called the base rate, all the other people, that dominates. Okay? This is the idea of updating beliefs, a rational way of updating beliefs. So we started believing there's a 5% chance Alex is a dev. The description fits developers better, 4 times more likely. But after seeing the evidence, we update that to 17%. Our belief went up, but not as much as our intuition suggests. Our intuition is biased. Because it fits, we just neglect the whole base rate. We just don't consider it. So let's look at the formula again. Probability of hypothesis given evidence is probability of evidence given hypothesis times probability of hypothesis divided by probability of evidence. Okay? pH is called the prior. Evidence given hypothesis is the likelihood. Probability of evidence is the evidence. And probability of hypothesis given the evidence is the posterior. We'll look at it again. How likely is Alex a dev before we have seen any evidence? That's 5%. If Alex is a dev, how likely is this description? 4 out of 10 devs fit. Okay? If Alex is not a dev, how likely is this description? 20 out of 200 creators fit. Lower rate, but so many more of them. Right? And this is how you get the formula. You don't need to remember the formula. I think the intuition is more important, but it's really interesting to think about that this is actually some bias that affects us in real life as well. Our biases are shaped sometimes like this. Okay? So we know that the probability of hypothesis given evidence using this formula, we can calculate. So only 70% chance Alex is a dev, despite fitting 4x better. The base rate wins. Okay. Basically the idea of how to visualize it is from a video by 3 Blue, 1 Brown. I put it in the website, but it's basically the same. I just changed the topic. It's very interesting. Please watch it. But again, I want you to remember this because in many different ways, this is a useful tool, a very important tool for data scientists, the Bayes theorem. There's actually a machine learning algorithm based on it as well. Okay. Now we are looking at probability distributions. Any questions so far? Am I going too fast? Yes or no? Seems like it's fine. So just give me a moment. I need to get some water. Okay. So now let's look at probability distributions. So far, we've been counting individual outcomes. By the way, these are all in your readings. I'm following basically in the reading of that book that y'all have to look at. Please read it. It's chapter 2, I believe. But sometimes we care about a summary value, like the sum of two die, right? How often does each sum appear? So sum 2, only one way, right? Sum 3, two ways. The most common, sum 12, only one way. Okay? So if we take all of these, count them all, but if we plot, this is what we get. This is called a probability mass function. In the book, I don't think it's using this properly. It's called a PMF, I think. And basically, each bar here is for discrete outcomes, and this gives you the probability of exactly that sum. All bars add to 1. So that is the probability of getting a 7, 8, 9, etc. So that's why when you throw two die, you know that 7 is more likely, so you can bet on that more likely. How to read it, basically it's used for discrete variables, values you can list and count. The x-axis shows each possible value. The y-axis shows the probability of exactly that value. The tallest bar is the most likely outcome. Easy to count. All bars sum to 1. Okay? There's another concept that's pretty useful. It's called the cumulative distribution, a CDF. For discrete, you can also think about each point is the probability of the sum is at most x. It's useful. You can say, okay, what is the probability that the sum is at most 7? So you look at this, and all of the ones before it also add up. You sum it. Okay? If you want to play Dungeons and Dragons, this is how you think about it, right? You throw whatever the dungeon master says, throw a a D8, and you need to get at least 12. I don't know. D20, you need to get at least 12. That's how you think about the probability. You need to draw this in your head for the nerds in the room, because you don't want to only get 7. But the probability of getting a D20, just a D20, is just that, right? So the y-axis is the probability of x smaller than that x, at most this value. The curve always increases. It ends at 1. All outcomes are at most the maximum. Deeper sections, more probability mass there. Okay? Flat sections, no probability mass there. Okay? So PMF versus CDF, you can get probably the same amount of information from them by just thinking about it differently. You can always convert. So what about continuous variables? Dice sums are discrete. You can list every possible value, but many real-world measurements are continuous, like height, for example. So you can be 162.3, 175.8, etc. You can be very continuous. Weight, temperature, reaction times to stuff. A lot of your research on data are continuous. They're infinitely many possible values, right? So we can't assign probability to each exact value, okay? So we can't say what is the probability of this. This is just because that's meaningless, that the probability is 0. So imagine measuring the height of every student in the university. Instead of asking, what's the probability of being exactly 170 centimeters? We ask, what's the probability of being between 168 and 72? So you can give a range, and then you can calculate the probability. A histogram, which groups these different ranges, helps. You can normalize so that a total area equals to 1, and it becomes a probability density function. The y-axis is density, not probability. So for a probability density function, you want to look at the shaded area. Okay? This is how total area under the curve. And the total area is 1. This is how you think about it. You don't read it like, you can't just draw a line here and say, oh, that's the probability. It doesn't work like that. Okay? So just to think about the key differences between PMF and PDF. It's about both about probability, but like for PDF, you look at density, right? You can read that one directly, but for PDF, no, you must compute the area. Probability of exact value can be more than 0, but the exact value is always 0. You read the bar, you compute the area. I just want to repeat here, and sums always integrate to 1. And the CDF for continuous values, though, looks similar. You can get, because it's the same idea, you can get the probability of height being less than 100. So you can have the same sort of, you can actually read it like you read the other one. Okay? And again, go back to the reading, but one of the more famous distributions is the normal distribution, where it's called the bell curve, where it's centered around the mu, like the mean, and then the spread is decided by the standard deviation, right? So smaller, it's more packed, tall and narrow, values cluster tightly. Larger, it means it's shorter and wide, values spread out. Most data falls within 2 standard deviations of the mean. So let's look at examples of heights. 8% of students are between 163 and 177. Although in reality, these heights are bimodal. Again, in my other course I teach it, we can talk about it because heights of men and women are different, right? So you get 2 modes, right? These distributions are bimodal, but 95% are between 156 and 184. 99.7 are between 149 and 195. So there might be someone that's 2 meters tall, that's more than 4 standard deviations away. That's very rare. It's called an outlier. So why does this matter? Many natural measurements are approximately normal. For example, when you report mean plus minus standard deviation, you're describing this shape. If your data isn't bell-shaped, that means it can mislead in a lot of these methods that we look at in statistics. Always plot your distribution before summarizing. Okay, that was our coverage of just the idea of probability distributions, just how we think about it. Descriptive statistic, essentially we want to summarize the data. That's where a lot of your first assignment will be, which will be published shortly in a couple of days. So we often don't look at data individually. We need numbers to summarize the data set. So for example, 2 main questions that we ask is, what is the center, the measure of centrality, and how spread it is, right? We think about 2 things. So imagine, for example, that we survey 30 students about their daily screen time in hours, okay? And then you get something like this. You have between 4 and 5. You see how this works, 4 hours. For some of us, it's legit 12 today. For me, it's been 12 hours actually. So this is long tail on the right. So there's a few heavy users. And that's how we think about the mean. The mean is something that I hope that you all know about. Essentially, is the sum of all values divided by the numbers, by the count. For example, the mean is 7.2 hours. But does that feel like a typical student? We don't know. The middle value when data is sorted is the median. Half of the students are above and half are below. The mean 5.2 is pulled right by heavy users. The median is more robust. So for example, this is like a visualization that we can show that the mean is very sensitive to outliers, right? If the heaviest user uses on their mobile phone 24 hours a day, which some of us are, even in sleep, we hold it and we listen to. I actually use it, so my screen time is close to 24. The mean would change. Okay. The mean essentially chases the outlier. The median barely moves. So for skewed data, the median is a better summary. Okay. Another way of just describing data set that gives you a lot of these ideas is a box plot. Shows 5 numbers at once. The whiskers are the range excluding the outliers. So the maximum and the minimum is here. The box is the middle 50% of the data, Q1 to Q3. These are quartiles. So Q1 is 20, Q1 is that 20%, 25% of data is less than this. 75% of data is less than this. The line is the median, the green line. And the dots are outliers that are beyond 1.5 times IQR. And the IQR, the interquartile range, is basically the range between Q3, the amount between Q3 and Q1. So you say, okay, 6.2 minus 3.8, and then you go 1 point times multiplied by that. What is that? And anything above that, you consider that an outlier. That's one way of thinking about it. Use box plot. This is a very useful method for describing your data sets. And it helps because you can use it and the outliers do not affect it, and you can think about it in different ways. What is the mode? Is the most frequent value in our data. 4.5 hours appears twice. Technically, that is the mode. But with continuous data, the mode is rarely useful. The peak of the histogram is more meaningful than any single repeated value. Okay? So again, summary, you should all know this. Mean is good for symmetric data when it's no outliers. You use it a lot for many different cases, but you need to think about that. It's affected by outliers. The median is used especially for skewed data, and the mode, you use it for categorical data. And when in doubt, you should generally report both mean and median. It's useful. The gap between them tells you about skewness. Okay? Another important idea is the idea of spread, which is the variability in the data. Standard deviation is the one that we use, okay? You can use this formula to calculate it. You basically get the difference between everything and the mean, and then you to the power of 2, and then you sum them, and then you divide by n minus 1. N is the total count of items. So it tells us how far on average our values from the mean. For our data, standard deviation is 2.6 hours. The shaded region shows mean plus minus 1 standard deviation. It's a very useful way to visualizing the data. Why do we do n minus 1? Again, it's explained in the book, because dividing by n gives the population standard deviation. N minus 1 gives the sample standard deviation. A sample of 1, if you just take one person, it tells you know nothing about spread. With n minus 1, one observation gives undefined, as it should be. For large n, the difference doesn't matter. So as the more you do the sample, the more you can trust your sample. Then we probably have a quantitative methods class or something that should go more into this. I need to just jump over all of this. In my visualization class, I cover some of this as well. So now, what's a low variance versus a high variance data? Low variance, as I mentioned, basically means everyone is more similar. So this is mean is 5, standard deviation is 0.8. This is mean is 5, standard deviation is 3. As you can see, there's a lot of people that are just around 5. This is way more spread like this. So the mean is the same, but you want to always report what's the spread. So there's this idea that is called Chebyshev's inequality that's described in the book. Essentially, with standard deviation, you can have a guarantee that at least 75% of the data is within plus minus 2 standard deviations, and at least 89 is within 3. And for normal distributions, the bounds are much tighter. It's 68%, 95%, and 99.7. And remember these numbers, because these are how we think about p-values and stuff, for example, because we assume the data is normal, and then we calculate all this stuff. I think next week we'll have to cover that. So this is a powerful summary. So mean symmetric data or median skewed data spread, essentially you use standard deviation, report both of them when you're doing descriptive analysis, and beware of outliers. They distort the mean and inflate the standard deviation. Okay, now correlations. I'm zooming, I'm speed running a lot of topics, so y'all have to read yourself a little bit, but just for us to have some base ground. What is a correlation? We say two variables are correlated when knowing one tells you something about the other. For example, you can say one increases, the other also increases. So more screen time, more apps installed. More screen time, lower GPA. The strength and direction of this relationship is what we want to measure. For example, the correlation between screen time and number of apps installed could be considered a positive one. As one goes up, so does the other. And points cluster around a rising line. So this is a positive correlation. Let's say the R is 0.85. Now, screen time versus GPA, as one goes up, the other goes down. So this is a negative correlation. Similarly strong, but negative, okay? But we have values that are, let's assume like screen time versus height. I don't think there's any reason for these to have any relationship. It doesn't mean that if your screen time is up, your height is high. Maybe there are some reasons for it, but we don't know. There's no pattern. The line is nearly flat. So knowing one tells you nothing about the other. And this is important, right? This is something that we're going to talk about, right? So just thinking about the correlation coefficient as Pearson, this is how you think about it. 0 means there's no correlation. Around 0.7 is a strong positive correlation, and 1 is a perfect positive. And around 0.7 here is a strong negative and perfect negative. How you think about it? R squared is a fraction of the variance in the data that is explained in Y that is explained by X. So when R is 0.8, R squared is 0.64. That means that it's 64% is explained. If it's 0.5, only 25% is explained. That's why you don't think that a 0.5 is a strong correlation, okay? And 0.1 is like basically nothing is explained. So weak correlations have very little predictive power. R drops fast. Don't be fooled by moderate values. Now, an important topic, you all have heard it, is that correlation does not imply causation. Ice cream sales, for example, and drowning deaths are strongly correlated. Does that mean that ice cream causes drowning? Maybe, but the R is 0.99. It's very related in these different months. Does ice cream cause drowning? No. Summer causes both. More people swim, so more people drown, and more people like ice cream. So these two are confounded. The heat, more swimming, more drowning, right? The heat, more ice cream sales, okay? So essentially, you're trying to look at a confound as a hidden variable that causes both observed variables. Even though they have a correlation, it doesn't mean that one is causing the other. There's a lot of examples, police presence. There's a lot of reasons why police presence might be high. One of them is that crime might be high, right? But there might be racist police or something. Medicine intake doesn't show that illness is high. Medicine doesn't cause illness. Sick people take medicine, okay? Establishing causation requires a controlled experiment. We're going to talk about that a little bit later. But remember the notion of controlled experiment. If someone says, oh, something is higher, these two are correlated, more often than not, you think that there is some association, but you don't want to take that as a causation. In the book, there's another useful way of calculating correlation is the Spearman correlation. It's useful because the Pearson correlation, which we're looking at, is it looks at a linear fit, misses the curve, right? But Spearman measures a monotonic fit, detects the relationship, gives Pearson is around one or something. Okay, so it's looking at a ranking between them. And a Spearman is also more robust to outliers. So essentially, if the correlation is linear, use Spearman. But if your data is not a linear, it's like more ranking. Maybe you have some ranking data, etc. You can use Spearman to get the correlation between the data. Again, in the book, there's more explanations of this. Okay. Lastly, logarithms. These are useful. One thing funny for me was that I never talked about logarithms in English. I never studied this in English, so it's really hard for me to teach it. But essentially, log x to the base of b, I believe that's how you say it, means that b to the power of y equals x. I hope that I'm saying it correctly, but y'all know what I'm saying. In plain English, how many times do I multiply b to get x? So in base of 2, log 8 is 3 because 2 to the power of 3 equals 8. In a base of 10, 10 to the power of 3 equals 10,000. That's how you calculate it. So exponentials grow very fast, logarithms grow slowly. So that's how you sort of a lot of times use them with exponential data, and they are inverse of each other. There are a lot of reasons to use logarithms, but in the book, there are 3 separate ideas. You can use them to multiply probabilities, basically convert products to sums of numerical stability. You can handle ratios, essentially make increases and decreases symmetric. And you can use it to normalize skewed data. Stretch the left, compress the right. So role 1, imagine a spam filtering, checking 10 words in an email. Each word has a small probability of appearing in a spam, right? With 100 words, these are really small. Floating point underflow. When the computer rounds this to 0. However, you use the logarithm. You take the log of all of them and sum them. And then instead of multiplying tiny numbers, sum their logarithms. And this gives you always negative because log of p is because p is between 0 and 1 is always smaller than 0. So that's useful, very useful information. By the way, I'm posting these slides. All of the slides will be posted on the website, so you can go and look at them whenever you need. The other, ratios are asymmetric. So if something doubles, ratio equals 2 to 1 is 2.0, right? So that's plus 100%. But if something halves, the ratio is 1 divided by 2 is 0.5. It's a reduction of 50%. These are not symmetric, right? A doubling and halving should cancel out, but the average of 2.0 and 0.5 is 125, not 1. So that's a problem. We want these changes, the ratios, to be symmetric. And again, this is really useful for thinking about outcomes in machine learning and stuff. So raw ratios are asymmetric, and there's more room above 1 than below, right? So here, the values can double, but if you have them, they're all here, right? So it's asymmetric. Points above the line are improvement, lots of space. Points below the line are decreases, cramped between 0 and 1. Hard to compare magnitudes above and below. So a ratio of 8 looks dramatic, a ratio of 0.1 doesn't, right? But when you take the log of the same data, then everything becomes symmetric. Log of 2 is 0.69, doubling. Log of 0.5 is minus 0.69, halving. So it gives us a very good way to compare these two things that should cancel out. It's symmetric. It gives us around 0, equal space above and below the line. A doubling and halving now look equally extreme. So when we want to say, okay, if something happened, the probability of something doubles, that's why it's important, right? We look at the log of the ratio because it's better. It's a better measurement. The other use for logarithms is for skewed distributions. So this is skewed right. A few heavy users pull the tail out. The mean is misleading. Hard to model with standard tools. So sometimes many real-world distributions look like this: income, city sizes, etc. So when you take the log of it, it becomes more central and symmetric. It's much more symmetric. Long tail is compressed, easier to model and analyze with many of our tools. Now, the mean is more meaningful. It's called a log normal distribution. And it's also, you can, when you take the log of something that grows exponentially on the axis, you can see that you can basically, you'll get a line. So when data has a huge span and you want to clamp it, you can use that. When you expect exponential growth, population, viral spread, etc., you want to model it, you can use logarithms. Comparing percentage changes rather than absolute changes, which is a very useful term. And maybe plotting ratios or probabilities. Maybe you want to do the logs. And if you want to get a straight line on a log scale, means constant percentage growth, a very common and important pattern in data. Like for the price of something, like 100% doubling prices, for example, all you want to look at. So log converts multiplication to addition, ratio is symmetric, and normalizes skewed distribution, pulls long tails, and log axis reveal exponential patterns as straight lines. When in doubt, with right skewed data, try taking the log. Okay, that's all. That's the math summary that we have. You should look at the book. I'm going to post some really useful videos for you to look at, especially on the base theorem and all the other stuff in our resources. Hopefully you take a look at it slowly as we do. Our course is not math heavy. We're not going to deal with this. It's coding heavy, but understanding the concepts will help you interpret a lot of these things that we talk about. Okay. Any questions? No questions? Was the presentation clear, understandable? This is the first time I'm teaching this course, so gradual feedback. If you want other ways, I'm trying a lot of new stuff, let me know. A lot of math stuff. That's a data science course, but you'll have access to this. Definitely, I'll suggest that you read you should read the book, chapter 2. Especially the first parts are really important. We're going to have quizzes on it, and it's not a hard read. So read it, and it'll help with interpreting data science stuff. I know sometimes it's confusing. Again, hopefully go back to the slides, read the book. For this course, even though you need to know some math for data science, otherwise, what's the point of data science? But you should think about these different things. Questions, Tashif, go for it.
How relevant are tree diagrams and probability in data science are in our course?
Probabilities?
Yeah, the tree diagrams and all.
Very important in interpreting model outcomes and machine learning outcomes. These are just important. So it depends on what type of data science you're looking at. We're gonna basically have a lot of sort of coverage, and this course, at least the way I teach it, focuses mostly on intuition of these different methods. At least I want you to understand how these are used and why they are used and what the meaning is and how you can run them. You need to also get a better understanding of some of the basics, and you'll slowly get that anyways.
Sounds good.
Okay. All right. If no questions, we can adjourn the class.